Hi there, Mr. Sutton here with the BC Calculus 618 Part 2 homework solutions on logistic growth. For this first problem, we're given this logistic differential equation describing the growth of a population of creatures, and we want to know, among other things, the carrying capacity and some other things that we'll get to later. So our carrying capacity, since this is already in Kp m minus p form, it's just going to be this m value of 200. And then for the size of the population when it's growing the fastest, that's always half the carrying capacity. So that's going to be half of 200, which is 100 creatures. And then finally, the rate at which the population is growing when it's growing the fastest. Well, we're just plugging 100 back into the differential equation to find that, since this already gives us the rate. So 0.006 times 100 times 200 minus 100. So this is going to be, let's see, 0.006 times essentially 10,000, which is going to be 60 creatures a year. For number 2, we've got a differential logistic equation giving us the rate of change for population of creatures. And we want to know, first off, the carrying capacity of the population. Since we're already in Kp m minus p form, carrying capacity is just going to be this m value right here, 4,000. And then the size of the population when it's growing the fastest, that's always half the carrying capacity. So for size, we've got half of 4,000, which is going to be 2,000 creatures. And to find the rate at which our population is growing when it's growing the fastest, we just have to plug the population where it's growing the fastest, 2,000, into our differential equation to get the rate of change. So plugging in 2,000 for p, I'm going to have to use the calculator for this. And the way these things work out, I'm essentially doing 0.0003 times 2,000 squared. So that'll be 1,200, and that'll be creatures per year. For number 3, we're given a population that satisfies this logistic differential equation over here. And the initial population is 3,000 apparently. T is time in years. We want to know the limit as t approaches infinity of p of t. So if you're asking for the limit of the population as we go on to infinity, you're essentially asking for the carrying capacity, since this is a logistic differential equation. But before we can find the carrying capacity, we want to put this in Kp m minus p form. It's almost in that form, but not quite, because we have p over 5,000 instead of just p over here. So I'm going to factor out a 1 over 5,000 from everything to get it in that form. So I'll have 1 over 5,000 p on the outside. And on the inside, 2 divided by 1 over 5,000, that's just 2 times 5,000, so 10,000 minus p. Now that means I have a carrying capacity of 10,000. So that means that we have E for our answer choice. For number 4, we're told that insects destroyed a crop at a rate of all this stuff, tons per day, and T is measured in days. To the nearest ton, how many tons did the insects destroy on the time interval from 7 to 14? Now, this is on a homework with logistic differential equations, and this looks kind of like a logistic function up here, although this variable in the numerator is kind of suspect, but we might be able to turn it into a logistic function. However, this is a calculator question, and they're giving you a rate of change and asking you basically how much of that destruction you accumulated over this time period. All we have to do on this one is just integrate this rate of change from 7 to 14, like so. So for this, we will use the calculator. So here we go. I've got my integral from 7 to 14, and I used alpha and then y equals to get my little fraction bar here. Because this is kind of messy to plug in trying to use parentheses. This assures me that I'm not putting anything in the wrong place. And then I'm using x instead of t, just I'm more comfortable with x. Enter. And that comes out to roughly 125. So that's going to be choice A. For number 5, we're asked which of the following differential equations for a population of p could model the logistic growth, and they spell it out. This is logistic growth, shown in the figure above. So for logistic growth in general, our differential equation is Kp times m minus p, where m is our carrying capacity. Now the m in this case is just going to be wherever we're leveling out when we go to infinity for the function. So that's going to be the 200 in this case. So we can write Kp times 200 minus p. Of course, I don't see anything remotely like that over here. If you look at all of these, it looks like the p has been distributed out, and certainly they didn't write k. They have actual numbers in here. So let's distribute out on this side. We've got, this will be 200 kp minus kp squared. And again, this doesn't look quite like anything we have over here because we have a k instead of an actual number. So we're going to have to figure out the relationship between these two coefficients here. And maybe that'll help us figure out which of these things to choose. So what I notice right away, first off, you have a p minus a p squared. So right away, that eliminates answer choices C, D, and E, at least assuming that k is a positive constant. So now we've got it narrowed down to A and B. Looking at these two coefficients, I notice that the p coefficient is 200 times the p squared coefficient. Well, let's look at these two answer choices. We've got 0.2 times 0.001. 0.2 is 200 times 0.001. The same cannot be said between 0.1 and 0.001. So choice A, then, is the only one that matches this relationship. For number 6, the number of antibodies Y in a patient's bloodstream at time t is increasing according to, keywords here, logistic differential equation. So which of the following could be that differential equation? So in general, with logistic differentials, we're looking for something in the format of Kp and times m minus p. Now, p is just the output of whatever the function whose rate of change you're given is going to be. So in this case, we would have ky times m minus y. So we're looking for something that's going to be in this format. So we need something that has a y on the right side of the equation, at the very least, right? So these two choices, A and B, that have t's instead of y's, these are no good. We'd also like something that has a parentheses with some number minus y in it. So choice C is also not very good. So now we've got it narrowed down to choices D and E. The only difference between these is that E has a y on the outside and D does not. In our general logistic setup here, we have a y on the outside, an output variable on the outside. So only choice E then matches this format, and that's what we're going with. For number 7, number of students in a school who have heard a rumor at time t is modeled by a function p, which is the solution to some logistic differential equation. At noon, we're given some other information out of here. Eventually, we want to know which of the following could be the logistic differential equation. So in general, logistic differential setup is going to be Kp times m minus p equaling dp over dt. So we essentially want to figure out the values of k and m that are going to match one of these answer choices. Okay, well, we actually know m already. There's only 500 students in this school, so that's going to be our carrying capacity, our limiting value on how many students have actually heard the rumor. So all we need to actually figure out is k. Now, in order to get k, that means we must have some value for dp over dt and for p. Now let's go back and read the question, the specifics here. At noon, 50 of the school's 500 students have heard the rumor. Also at noon, p is increasing at 20. So we know that when dp over dt equals 20, p itself is going to be 50. And we also know that m is 500. So let's plug all of that in. So at noon, we have a rate of 20, 50 students, 500 for the whole school. Let's solve for k in this mess here. So we've got k times 50 times 450. Multiplying that out, I have 22,500, and then I'll divide both sides by that. So we have 20 over 22,500. That'll be our k value. Now looking at my answer choices, that doesn't match any of them, so we need to reduce it. You could probably guess which one it reduces to, but if you're not sure, this was a calculator question, so you can reduce it on the calculator. So to do this quickly, I'm going to go to alpha y equals and get my little n over d fraction format, and I'll just write in 20 over 22,500, and if I press enter, it reduces it for me. That'll be 1 over 1,125. So plugging in our k value, we have dp over dt equals 1 over 1125p times 500 minus p, which gives us answer choice A. For number 8, the number of students in a cafeteria is modeled by a function p that satisfies this logistic differential equation, and they're telling us P of 0 is 25. We want to know the greatest rate of change in students per second of the number of students in the cafeteria. Since this is a logistic function and it's already in Kp m minus p form, we know that the max rate of change is going to happen at half the carrying capacity, essentially in the vertical middle of this thing. So that would be at P equals 200 over 2, or just simply 100. So that's not actually the max rate of change. That's where the max rate of change happens. So be careful, don't pick choice C just yet. We actually have to plug 100 back in to the differential equation to see what this comes out to. So this is essentially 100 times 100, so 10,000 over 2,000 is going to equal 5 students per second. So that would be answer choice A. For number 9, we have a population modeled by a function p, which satisfies this logistic differential equation. Based off of this, if p of 0 is 3, we want to know the limit as t approaches infinity of p, and pretty much the same thing if p of 0 is 20. So the key on this, we're going to first put this in standard logistic form, which is just kp times m minus p. So I'm going to divide or factor out a 1 over 12 to make this happen. So on the outside, I'll have p over 60. On the inside, I've got 1 divided by 1/12, which is just 12, and then minus p. So it's a little bit easier to look at this because in this format, this number right here, whatever p is being subtracted from inside there, that is your carrying capacity. So we have a carrying capacity of 12. And we know with logistic functions that the original function, is always approaching this carrying capacity as you move toward infinity to the right side. So if we're starting at 3 and then going to infinity, your population is going to be approaching 12. And even if you're starting above the carrying capacity, because 12 is a horizontal asymptote for the function, as you move to the far right, even starting up at 20, you're still going to be approaching 12. For part B, they want to know if p of 0 is 3, for what value of p is the population growing the fastest. So this is always going to happen at half the carrying capacity. That's where you have that inflection point. So this is going to be half of 12, which is just 6. For this problem, we have a different population modeled by a function y that satisfies this separable differential equation. Based off of that, they want us to find y of t if we have an initial condition of 0, 3. All right, well, they told us it was separable, and we kind of know we need to do it anyway because we see y in the differential equation. So we'll start by separating the variables. I'm going to divide both sides by y, so I have 1 over y dy on the left. And I'll multiply by dt to get that over to the right side. I've also still got this random 1/5 over here. I'm just going to distribute that in here so I have less things to worry about. So this will be a 1/5 minus t over 60 dt. And now let me go through and take my antiderivatives. So on the left side, I've got ln absolute value of y. On the right side, I've got, this will be a 1/5 t. This is going to be, let's see, this bumps up to a 2. Dividing by that, I have minus t squared over 120, or 1 over 120 t squared. And then don't forget the plus c. Next, I'm going to plug in my initial condition they gave me to figure out the value of c. So on the left side, I've got ln of absolute value of 3, which is just ln of 3. Over here, I've got 0 conveniently plugged in for anything with a t. So that zeroes out everything on the right side except for c, which means that my c must have a value of ln of 3. All right, it's time to now go back and plug this into our general solution here, but we have to resolve this absolute value before we go any further. Since y equals 3, that means that y in general is positive, so I don't need this absolute value. I can just replace this with just ln of y. And I have the rest of this stuff that I had before, the 1/5 t, the 120 over t squared, and now I've got my plus ln of 3 for my c value. Just have to isolate y, which I can do by raising e to both sides. So I've got y equals all e to all that stuff. And if I wanted to be really fancy, this ln of 3 can actually come out as a 3 coefficient because we could split this up into times e to the ln of 3, which is just 3. So that's about as simplified as it's going to get. For part D, they want us to figure out the limit as t approaches infinity for the y that we just found in part C. So here is that original function again, just redisplaying what you did in part C. And the key on this one, right away, you have to realize this is not a logistic function. It's tempting to just say that this is going to equal 12 because that's the carrying capacity. However, there is no such thing as carrying capacity on this. We don't have a logistic. So we're going to have to do this the old-fashioned way. I think the easiest way to do this is to turn this into a fraction using our exponent rules, and then use the choose your champion approach when you have limits that approach infinity. So I can rewrite this as e to the t over 5 divided by e to the t squared over 120, and then this ln of 3 comes out as a 3 in front of the e that's in the numerator. So we've got 3e to the t over 5, and then e to all that stuff down there. Now as x, or in this case t, approaches infinity, which of these sides is growing faster? Well, we have two exponential functions, so they're both growing pretty fast. But if you look at the one down here, we have a t squared in this exponent and only a t to the first power in this top exponent. So that means that our denominator is actually going to be growing faster. Since our denominator is growing faster, that means that this fraction is getting smaller and smaller and smaller as t approaches infinity. So we can then say that the limit of this is going to be 0.